This is slide number 70 and I am your presenter Asloob Mudassar. Harmonic correlator. Rotation invariance can be demonstrated theoretically and experimentally using representation of input object O at the zeta and eta coordinates in circular harmonic function. First, the object O as a function of zeta and eta is represented in polar format, that is O as a function of r and theta, where the object is periodic in theta. That is O as a function of r and theta is equal to O as a function of r, comma, theta plus minus 2 pi. The Fourier expansion of object O as a function of r and theta using the variable theta is given below, as given in equation number 49. So we have represented O as a function of r and theta, that is its polar representation in terms of the Fourier expansion, which is the summation over m from minus infinity to plus infinity. We have OM as a function of r multiplied by e to the power iota m theta, where OM of r is the mth Fourier coefficient and is defined below as given in equation number 50. That is OM as a function of r is equal to 1 over 2 pi, integral from 0 to 2 pi, and the integrand is O as a function of r and theta multiplied by e to the power minus m theta, and the integration is with respect to d theta. Each term on the right hand side of equation number 49, that is this equation, is known as the circular harmonic term. When the object is rotated counterclockwise by an angle delta, equation number 49 takes the following form. So see, in equation number 1 we have shown the same equation as equation number 49, but when the object was rotated by an angle theta, by an angle delta. So we have this equation over here, and you know on the right hand side of equation number 51 we have separated the phase factor e to the power iota m within the bracket delta of theta minus delta into two parts, that is e to the power minus iota m delta multiplied by e to the power iota m theta. And you see that here delta is what gives you the information about the rotation of the object. It follows from equation 51 that when the object is rotated, each term in the expansion suffers through a phase change of a minus m delta, because minus m delta appears in the exponent. The cross correlation in polar format between the object O as a function of r and theta and its rotated version given by O as a function of r, comma, theta minus delta is defined below. You know that in the correlators we measure the autocorrelation. So you see that we want to evaluate the autocorrelation of the object O, which is unrotated, with its rotated version. So this is the autocorrelation given in equation number 52. And on the right hand side we have the integrals, which gives the definition in polar coordinate systems. That is the autocorrelation definition in polar coordinate system. You see that we have the radial part, and the integral is there for the radial part of the integral, and then we have the azimuthal part of theta from 0 to 2 pi, and you know that the integrand contains the complex conjugate of O, which we call as O star as a function of r and theta multiplied by O, which is the rotated version of object, that is O as a function of r, comma, theta minus delta, and the integration is with respect to d theta. So this is the autocorrelation, and this is what we want to measure, and we want to extract the information for the rotation of the object. Well, you know that here we have O star, that is a complex conjugate of O, which we are going to replace using equation number 49. So we shall take the complex conjugate of both sides of this equation, and then we shall plug in the right hand side of this equation into equation number 52. So use of complex conjugate of both sides of equation number 59 into equation number 52 gives the following equation. So we have the autocorrelation in the symbolic form, that is O r of theta, star stands for the autocorrelation, autocorrelated with O as a function of r, comma, theta minus delta, and the definition in integral is given. So we have this definition in the integral form, and the only difference between the previous, that is in equation number 52, and this the current this part, that is the second step of this equation, is that we have replaced O star by its value on the right hand side from equation number 49. So we have placed that value over here. And you know that in the third step that is given in red, we have rearranged the terms. That is, we have separated the angle, we have separated the integral, which is the integral on theta, and we have the integral on r. But you know that these two integrals are not separable completely, because they are linked, because the linkage is provided by the object O as a function of r comma theta minus delta, because it contains the information, it has a information of both as a function of r and theta. So you see that the integrals are not completely separable. But here we have separated the theta dependent integral, not completely but partially, and the radial integral is given on the left hand side as shown in the red, that is in the third step. And in the next step, which is the blue step, what we have done is that we have introduced two terms over here, e to the power minus iota m delta and e to the power plus iota m delta, shown in green color. So these two factors have been introduced. One is within the integral and the other is outside this integral, that is the integral on theta, so that we can combine these one. So you see that in the next step we have combined the exponents within the integral. That is, we have on the rightmost side we have integral which is on theta, that is we have 1 over 2 pi from 0 to 2 pi, limits of the integral O as a function of r comma theta minus delta, and then e to the power minus iota m, within the parenthesis we have theta minus delta, and we have written d theta as d of theta minus delta, because the delta is a constant over here, so the derivative of delta will be equal to 0, so it doesn't matter. So you see that we have transformed the theta dependent integral in this form. It means that we can replace this integral by the value of OM as a function of r using this equation, that is equation number 50. So you see that in the equation number 50, look at on the left hand side we have r only, independent of the value of theta. And on the right hand side we have theta dependent, because we are integrating with respect to theta. So the theta, after the integration, theta will disappear and only the answer will be in the form of r dependent quantity. So you see that in the integral, note that theta in the as a function of O appears as a variable in the O, that is O as a function of r and theta. So theta appears over here, and then again the theta appears in the exponent form, and the theta appears in a d theta. So if theta is the same in all the three places, then even we can replace equation number 50, and which is the case over here in this you see that integral, that we have theta minus delta at all the three places. So we can replace this integral with the value that is OM as a function of r. Now you see that we have OM star and OM, so we can write it as the OM absolute square of OM, and then we can separate out the radial integral, that is a integral on the variable r. So we have let me read the total values in the last step. So the autocorrelation is equal to 2 pi multiplied by the summation of m from minus infinity to plus infinity, and we have e to the power minus iota m delta, which is shown in green, and then we have the integral 0 to infinity r, and then the absolute square of OM of r and with respect to dr. So this is the equation number 3, which is the last step of equation number 3. So you see that this autocorrelation which we have evaluated between the object and its rotated version depends upon these quantities. You see that the angle theta appears over here in the form of the phase, that is e to the power minus iota m delta. So it means that this delta, if we can extract this delta somehow, then it means that we can evaluate the rotation between the rotation angle between the object and its rotated version through the autocorrelation function. and this this integral which is depending upon the radial which has a radial dependence, this integral will give you the magnitude of the autocorrelation peak. So the integral will give you the magnitude of the autocorrelation peak, whereas e to the power minus m times delta, which is the phase factor, will give you the information about the rotation of the object in the correlation, in the autocorrelation peak. That is the object O, and its that is the autocorrelation of the object O, and its rotated version can be extracted using equation number 53 at the last step. If we can extract this phase information, that is e to the power minus iota m delta, because this is the phase information which will give you the value of delta, and the other quantity, which is the integral, will give you the magnitude of the autocorrelation peak. It is obvious to extract the phase term e to the power minus iota m delta digitally, and thus rotation angle can be determined. It is important to discuss the optical implementation of this method, which we describe in the following words. First, prepare an optical transparency of the mth harmonic, that is OM of R e to the power iota m theta, of the given object O as a function of R and theta, using digital techniques. So first of all, we have to prepare an optical transparency using for the mth harmonic of the input object. Place it in the coherent processor and prepare its matched filter on the photoglass or on the glass plate or on the photoglass. So you see that up to this point we have constructed the matched filter of this object. Now present the input O as a function of R and theta to the same processor, either through digital or optical means, with the matched filter at its Fourier plane. The correlation peak at the image plane will have a magnitude proportional to this one, as we have shown over here in this equation. So the same integral, so our magnitude of the correlation peak will be proportional to this integral over the variable r, and thus will be independent of the rotation of the object. That is, the magnitude is independent of the rotation. But you know that in the autocorrelation, apart from the magnitude, we have this phase vector e to the power minus iota m delta that will remain there. So you see that we can extract delta from here through the autocorrelation peak. However, the magnitude of the autocorrelation peak will be independent of the rotation, but you know that the phase of this autocorrelation peak will help us to determine the value of the angle of rotation, that is the delta, can be extracted as we have mentioned over here. That is the phase term delta can be extracted digitally, and then the rotation angle can be determined. An extension to an optical coherent processor that could convert the input transparency O as a function of R and theta to its circular harmonic representation given in equation number 49, would be required to perform the rotation invariance based on circular harmonic representation of the input object. So it means that we need an extension to the optical coherent processor, because we want to convert the object O to its harmonic form, to its m harmonic, using optical means. So for that one we need an extension to the optical coherent processor, so that we can do the implementation that we have mentioned over here. That is, first prepare an optical transparency of the mth harmonic of the given object. For that one we need an extension to an optical processor that could perform this task. So that would be required, so that an extension to an optical system would be required to perform rotation invariance based on circular harmonic representation of the input object. Further details on other correlator will be covered in the presentations on the course on advanced topics in Fourier optics by this author, that is by Asloob Mudassar. There are many advanced topics in Fourier optics that need separate attention in much greater detail and require separate representations on such issues. So see you on new topics in the next presentations. So this is the end of slide number 17.